Chapter 4, Section 15, Osmolarity and Microbial Growth. Now, water. Water is going to be the great equalizer here. How much water? Where is it? Where is it going? Is it moving into the cell? Is it moving out of the cell? Osmotic stress can be something that most microbial cells, prokaryote, protist, fungi, are gonna have to battle against. The osmosis, the osmotic effect. Where's the water? Water always moves from high to low concentrations, low to high solute concentrations. That's something a lot of students forget. That if there's a lot of solute, that means there's low water. It means water is going to move in, cause the cell to swell up. So when you look at water activity, the osmolarity, pure water, 1. Human blood, 0.995. Strep, E. coli likes that level. Seawater, there's not that big of a difference between our blood and seawater, but it's enough that strep, E. coli aren't going to handle it very well. It's going to be a little harder on them. You start getting to stuff, salami, certain cakes, jams, salted fish. Well, now the level of water there is going to, the solutes, usually it's going to be salts. Other additives are going to be such that microbes cannot grow. That's why salami, other cured meats that have a high salt, high nitrate, and things like that, low water, makes it hard for things to grow. The E. coli, the Vibrio, the Pseudomonas that would normally make these things, these meat products, start to, rot. Well, they can't grow there because there's not enough water there. The osmotic pressure there, because of the solutes, the salts and whatnot, make it just too hard. Microbes are going to grow, and a tendency to grow in places where, the water is going to be more of a positive balance. Water going in, just a slight tendency for the water to go in, well, they're going to do better, okay? Because their peptidoglycan layer or their dual membrane layers are going to hold their shape. So yes, they're going to have a little more increased internal pressure, but it's better than the other where water's leaving and, well, now the cytoplasmic membrane is starting to contract, pull in. And there's only so far it can contract, pull in before the cell can be damaged. One of the things we find that really drives the solute concentrations is salt, sodium chloride. There are microbes that like salt, high salt, low salt, or they just tolerate salt. Halophiles, halotolerant, extreme halophiles. How much and where, will drive who can grow there. I mean, you go through and you look, different solute concentrations will drive who can and cannot grow there. Salt lakes, cyanobacteria, halotolerant like staphylococcus. This is going to be one of the things we use as a selective pressure in labs. Mannitol salt, high sodium chloride concentration means that staphylococcus can grow, but most other gram-positive, gram-negative bacteria can't. Non-halotolerant basically can't handle a high level of salt. E. coli. As you get more tolerant, halotolerant, they don't like it, but they can tolerate longer. Staph aureus. Halophiles and extreme halophiles, they basically need it to be salty. It's not salty enough, they just can't grow. Staph can grow. It's not using it. It's not using the osmotic pressure. It's not, it just can handle it. Think about it. As I said in the previous lectures in this chapter, Staphylococcus is growing on the surface of our skin. So that's why it is, its, optimal temperature was, 35 degrees Celsius. Well, what else is happening on our skin other than a lower temperature than our core temperature? You're sweating, and your sweat's going to be lots of salt. So Staphylococcus aureus, that's been growing on mammalian skin for so long, has been selected for being halotolerant to our increasing levels of saltiness on our skin when we sweat. Other solutes that can drive osmotic stress, sugars, how much high and low sugar. Yeah, sugar. You would think, oh, more sugar would be great. They can handle. No, sugar cured hams. You put them on, you take a ham, coat it in sugar, put it in a smokehouse. The smoke keeps away the insects. The sugar dries out the ham, keeps most microbes from being able to grow on the ham, cause the ham to spoil before it can dry out and cure. Okay. Certain solutes, are not going to inhibit if they're water soluble. Some sugars, alcohols, glycine, what was that? Potassium chloride. They're not going to alter the movement of water because these are in solution. If they get too high, can they? Yes. If they're not completely water soluble, oh, most definitely. So you have to take into account not only what solutes you're looking at, but do they play well with water and what they're doing in the water. Are they going to be driving osmotic pressure? Hypotonic, hypertonic, isotonic? Are the organisms that are going to be there halotolerant, non-halotolerant, and whatnot?